So thank you very much for our presentation. Okay. So, dear presidents, dear all, first of all, I would like to say a huge thank you to CFMS for booking a slot for CFMS jeunes, like young researchers, and so I'm happy to present the work done during my PhD to this assistance. So thank you very much for this opportunity. Regarding the outline of the presentation, I will first present soil nailing, so I will try not to be redundant with Professor de Buan. And then I will introduce the Prosper software, which is a software I used during my PhD and which is not widely distributed. So I will take some time to talk about it, to understand the problem we were facing at the beginning of my PhD. And then I will try to describe the method we used to better understanding the mobilization of nails in a soil nail wall. This work included the experimental part, which was done in centrifuge in Nantes, in the Nantes campus of Université UCFL, and a finite element parametric study. And in the end, combining all these results, we tried to propose an adaptation to the Prosper software who aimed at a better design of facing of soil nail walls. So, to begin with soil nailing, I will just do a bit of history. The idea originated from the Austrian, what is called the Austrian method for tunnels, which consists in rock bolting, let's say. And it was adapted to nail the soil in place. And the first, to my knowledge, the first example was done in 1972 in Versailles to enlarge a railway station. But then it became soon popular, and there was the need for recommendations. So, yes, this need for recommendations appeared in Germany and in France. The first monitored soil nail walls was in Germany. I mention it because here in France we always talk about Clowter, and we sometimes forget Boden-Vernagelung. However, it was quite important, and it has been a key reference for later publications, even if the scope was maybe smaller than the one of Clowter. As an illustration, here is a picture from a PhD thesis wrote in 1993, there is a mistake, by Tay. He did centrifuge modeling of soil nail walls, and at that point, his reference to check that his model was relevant, his reference was the gas layer experiment from Boden-Vernagelung. So then we have the publications of Clowter, Clowter 1 in 91, the wall showed by Professor de Buan just before was instrumented inside the Clowter 1 project. In 2002, there was a second project, Clowter 2, which was published because the Clowter 1 didn't let some unresolved problems, and among them, especially, was the design of the facing. So it has always been a quite difficulty about soil nailings. And the question of designing soil nail walls is still relevant today and still an actual problem, let's say. In 2018-2020, there was a large reviewing of the standard about not only soil nail walls, but reinforced soil retainment walls. And so I was happy to contribute, even to a small extent, to this reviewing committee. So what exactly is soil nailing? It's not, sorry, it's done with the soil which is in place. You are not bringing backfill. So first of all, you excavate one lift, then you put the nail in the soil. The pictures are 1, 2, 3, 4. You put the nails in the soil, and then you put in place the facing. The facing is very often shotcrete, which is concrete projected. But we should also mention that other possibility exists, and some companies now develop prefabricated facing, which is a way to reduce CO2 emissions and also to improve the quality of working people, the ease of working people. So what I said is it's not, it's a type of reinforced soil, but it's not exactly the same thing as mechanically stabilized earth, even if they are very often presented together, because in the end, you have a soil with a reinforcement rather regularly spaced, but the phasing is really different. As I said, for the soil nailing, it's an excavation process, and for the MSC walls, it's a backfill process. In both cases, the anchors are passive. It means there is no pretension. So when you put the nail in place, they have no tension, and their tension is only due to the next phases. For MSC walls, it's the tension, the nails or the inclusions are activated by the next backfill layers. But for soil nailing, the activation of nails, of inclusions, is done by the next excavation of lift. Here's just an illustration of what I said before. It's a project done in Dublin, where they monitored during the construction of the metro project, they monitored the tension in lots of nails. And yeah, you can just see that once the nail is put in place, its tension is it's 0. And the major effect is done when you excavate the second lift. The tension increases a lot. The third lift also increases the mobilization of the nail. And the 4th and 5th lift do almost nothing. So the phasing is really important in the mobilization of the nail. Okay. So it's just an example, but it illustrates quite well the idea. Now I'm moving towards the way we design soil nail walls, and traditionally we are using the techniques of stability analysis. So it pertains to the Coulomb rationale as presented by Professor Salençon. It's not the rigorous framework of yield design, but the idea are here. So we distinguish the driving forces and resisting strengths. So the driving force is the weight, and as stated before, the resisting strength comes from the soil and from the nails. Then you write the equilibrium, you say it must be compatible with the strengths, it gives you constraints, and in the end you have an optimization process to tighten the constraints. For example, you will look at different failure surfaces or different mobilizations of the nails. So yeah, as I said, it's not rigorously yield design, but still it fits, I think, in a Coulomb symposium. So let's consider a given wall of width B and 8H. You will consider different failure surfaces. So this list has already been mentioned. In the software I use, Prosper, all these kind of failure surfaces are available, and you can also choose another failure surface. The only condition is that this failure surface must be convex or concave, depending on which side you are. but you cannot have a changing of convexity. However, if I talk about the limitations of this approach, we never consider the shear zone observed in Clowter. So the driving force, as I said, is the self-weight of the failing mass. The strains come from one side from the soil, and on the other side from the nail. So in the soil, it will be the more Coulomb criterion, and in the nails, it is a big question, as we understood. I said that in common softwares, so at least to my knowledge, homogenization and multi-phase model are not very often used, and the general approach is generally mixed modeling, where you use generalized stress, NVM, and so here our question is to find the maximum value that NV and M can take in order to know the maximum strengths you can mobilize, maximum resisting strengths. So to do so, what is generally done is to use what is called multi-criterion. You combine 4 criterion. It's in French. Let's say it's a bilingual symposium. So the first criteria, which is just the strength of the steel. The vertical line is the pull-out criteria of the nail pull-out resistance. And the 2 other criteria are either the plastification of the soil under the nail, like the butter knife. And last criteria is the development of a hinge in the soil, which induces plastification of the soil. Hinge in the nail, which induces plastification in the soil. So you combine these 4 criteria. It gives you a line in the plane. So I did not mention that here we consider the bending moment is 0. In the plane shear force and normal force, you get a line, and the question is which value do you take out of this line, because you have an infinity of couples Tn. And to choose it, generally we use the principle of maximal work by Hill, which allows us to choose one couple on this failure surface. So this is the way most of software, simple software, are deriving the tension in the nails. And in the 90s, in LCPC, they tried to develop something else, which was called the displacement method, but I will later on call it the Prosper method, because the word displacement will appear too much in this presentation, I guess. So their goal was to get the real mobilization of nail. So clearly we are making a step aside from limit equilibrium, and we are introducing mobilization of nails. But yeah, the idea was to imagine a displacement of the failing mass, to toggle, to play with to play on the mobilization of nails. So this displacement delta is a way to mobilize the nails, and it will become an optimization parameter, a parameter for our optimization process then. Of course, it varies between a given range. So yes, how do we deduce the tension in the nail from the displacement of failing mass? It's, let's say, simply an integration of the beam equation along the nail, and it uses the results of laterally loaded piles done also by LCPC. So once you integrate the beam equation, you are able to know the generalized stress in the wall beam, and especially on the failure surface. So you can take the value of T and N on the failure surface and include them in your comparison of driving forces and resisting strands. I said it's not a kinematic method because actually it's rather a static equilibrium, and the displacement delta is not a real displacement. It's mainly a way to mobilize the nails. Yes, and since we have the beam equation, which is integrated on the wall length of the nail, you are also able to know what are the tension at the facing. So not only on the failure surface, but also at the facing. And here, the idea of Prosper developers was to use the same tool to provide the analysis of stability of the wall and also an input for the design of facing. The idea was that since you know the tension in the wall nails, you can also know the tension at the facing, and it will be your input forces to design the resistance of the facing. So, for example, we get this kind of results. The nail tensions are at the facing. This wall is an experimental wall built just before my PhD. And so we put it in Prosper to imagine the distribution of facing tensions, and it was not very conclusive. Especially the last nail, the bottom nail, is the most mobilized. And in reality, we know that since there is no further lift, this bottom nail does not, it should not be mobilized. And if we compare to what is in the literature, we see that the profiles of the shape of facing nail tensions in literature is very different. Here we have two curves. One is from Cluter, the blue one, and the orange one from Bodenferner-Gelung. So it's clearly not the same picture. And it was also not in accordance with the tension we measured in situ, even if we had the high uncertainty in situ. So clearly the problem is we don't get the right shape of tensions, mainly because we don't take into account the differentiate mobilization of nails due to the phasing. So the idea for the rest of the presentation is to try to use a different delta for every nail and to say to take into account this differentiate mobilization. However, it's not easy to guess the shape of delta, and in the initial version of Prosper, it was possible to induce a variable delta, but by ignorance, we did not know the shape of delta, so it was not used. And the idea here was in the PhD was to find the shape of delta to use to. So the shape of delta relates to the mobilization of nails. So how did we process? The first idea was to use centrifuge modeling. So here also I will just do a very short history because we talk about centrifuge modeling, but we maybe sometimes do not know what is the main principle of it and where does it come from. So the idea is quite old. It's described in 1869 by Edward Phillips. And the idea was that if you want to do a reduced scale models, since soils are highly nonlinear, you still want your soil particle to undergo the same stress and strains as in the real prototype scale. So if in your reduced scale model you have a particle which is 10 centimeters below the surface, it has to undergo the same pressure as the sand particle 10 meters below the surface. So the weight of 10 meters of sand in the prototype has to be the same as the weight of 10 centimeters in your reduced scale model. So the idea is simple. You increase the gravity by 100. So that was said in 1869. It it was not, so the idea was simple, but the practice is not so simple. The first geotechnical application is in 1931, and the first, let's say, the first bright application which gave conclusive results was in 1936. And then we had to wait until 1982 to have a soil nail world modeled in centrifuge. It was realized at 1G, which means they built the centrifuge, they built the reduced scale models outside of the centrifuge, and then they put it in centrifuge, begin to spin. So the stress pass is not the real one, because all the phasing, the construction phasing is done at 1G when you have no similitude between the stress in the prototype and in the model. Later on, Tay in Oxford realized in-flight excavation by the use of a bag of fluids which were emptied during the flight. So it was quite a clever idea, even if you can notice a small problem, which is the fluid is not the same thing as the soil, and the K0, the pressure at rest, it's always 1 in the fluid, which can be a limitation, but still it's the first idea of in-flight excavation in centrifuge. So the in-flight excavation is clearly the most difficult part, but it's also crucial to respect the construction phasing and to give relevant results. So that's why we try to do it using really soil. So we use the motor and a geotextile wrapped around the axis of the motor, and the geotextile made some turns around the soil. So when you launch the motor, it wraps the geotextile around the axis, and step by step you reject baskets of soil. So we managed to get in-flight excavation with a real soil with this process. Another question we had regarding the relevance of our model was the similitude of behavior between the reduced scale model and the real one. As for the soil, I talked about it later, and as soon as you respect the scaling laws, you don't have any problem. But for the nails, and especially for the interface between soil and nails, we have, the centrifuge modelers have a catalog of scaling laws, and it states that if you want to be certain you have a scaling similitude, you need to at least have 80 grains of sand around the perimeter of your pile or nail or inclusion, let's say. And here I did not have this number of grain, because even if we use a quite fine sand, still our nails were really small, so we were at the limit. And to check the relevance of our physical model, we did some modeling of model. It means we did pull-out tests of our mini nails using a shear box apparatus. And first thing we checked was the repeatability of our test, which is, let's say, not so bad. So we said, okay, we can say we have a friction law between the nail and the soil, which is already a good thing. And second thing is the scaling law is not so stupid, and it corresponds to something you can observe on real scale nails. So yeah, we were quite confident about the relevance of our model. So just talking about the monitoring, we used optic fiber in the nails and digital image correlation of the sound. So we had a translucid glass to take pictures of the sound. This GeoPIV process developed by Stanier et al. Allows to know the displacement of the soil, the displacement field, and also to compute the strains by derivation of the not only by derivation of the sound, the strains are also corrected during the process of digital image correlation. So we get this kind of results. We had in the nails, we can again see that the nails are mobilized progressively with different lifts, excavation lifts. And we can also observe when we look at the strains, the color map. Red is the maximum strain and blue is zero strain. We can observe that we don't have really a slip line. We can even say that we have two nested slides. At least what we can say is we have a quite complex kinematic. We can also see that the maximum value of tension in the nails are not really aligned. It is, let's say, consistent with the fact that we don't have a single failure surface. So we have this complex kinematic, which once again highlights the importance of phasing, of construction phasing, and also it says that we cannot use the observed displacement in the centrifuge to put them in Prosper as a mobilization function. I did not talk about it in the presentation, but in a previous article in Revue Française de Géotechnique, we also showed that we have a high influence of the slenderness ratio of the wall. Even when you are stable, the settlement of the wall is highly dependent on the slenderness ratio of the wall. Okay, so I will go very briefly on the numerical model we did. After the centrifuge, we did a numerical model, which is a 3D model, but we only model one, let's say, slice of our wall. We used hardening soil models for the soil, and the nail were frictious beam elements, which means we had an additional degree of freedom, which is the relative displacement between the soil and the nail. And we used a quite simple law for the hardening soil model. Since Emmanuel Bourgeois said yesterday it was satisfying, I think, okay, it's good. Okay, we used, of course, the construction phasing. Our measurements were in accordance with the centrifuge results. And then we did a parametric study of about the slenderness ratio. So we had soil nail walls of different heights and different nails, giving different slenderness ratio. And the question was, what is the influence on the facing loads? Even if you look at only one soil nail wall, during the excavation process, actually what happens is you increase the slenderness ratio because the length of nail is fixed, and when you excavate, you increase the height of the wall. What you see is you go from a, let's say, round shape to something which I call pear-shaped, and ultimately it would be a triangle. So the shape of the tension is going from a homogeneous distribution to triangular one when the wall is more slender. So we did it for different walls, and we observed that if you divide the tension by their maximum value, so you look only at the shape of normalized tension, for whatever the height of the wall is, for a given slenderness ratio, you obtain the same profile of facing forces. So the shape of the facing loads, is, let's say, dependent only on the slenderness ratio, also on soil parameters, of course. And it's something which is quite consistent with the literature review, again, because I did not mention it before, but in Cloutaire we had, let's say, a bulky wall with B over H equal to 1, and in Bodenvernagelung it was a more slender wall, and you see that the comparison fits. For the slender wall, you have a triangular shape, and for the bulky wall, a round one. Okay, so now if I go back to my initial question, what shape of delta should I use? We tried to think this way. We said, okay, the bulky walls have homogeneous tension. The slender walls are something more pear-shaped, and eventually, if you go to no nail, like B is equal to 0, you have active thrust, and you have a triangular shape of tension. So the idea is the bulkier the wall, the further it gets from active earth pressure, which means the effect of nails is to go far from earth pressure. And my idea was then to say, okay, I can characterize the mobilization of nails, the effect, by this distance to the active earth pressure distribution. So by distance, I introduced the distance, I called it the ratio between what is observed at the facing and what we would observe in a case of active earth pressure. The shape is known to be a function of B over H, and I took this function as a polynomial of order 3 in order to be able to capture the transition from a round shape to a pear shape. By linear regression, we get the coefficient of the polynomial. So here, my guess was to say the function delta, which gives the mobilization of nails, will be given by this formula. I introduced it in Prosper. I'll do it later. I introduced it in Prosper, and it gave a more suitable shape. So I already went a bit further than my time, so I don't know. Okay, so just I want to show that we went a bit further in the parametric analysis, because the first parametric analysis was only about was for fixed parameters of soil. So we introduced the relative stiffness of the soil, and I introduced a parameter which indicates the shape of the facing tensions. And if I plot the ISO line of this parameter in the plane slenderness, stiffness, I get this abacus. And this line is the reference equation I gave just before. And if you have a soil which is a bit stiffer, you can go back to the reference equations following the ISO line, and you will apply the reference equation for adapted slenderness ratio. And so that's what I applied to get better results on this real wall. So yeah, the conclusion is that it's important to consider the phasing when you design geotechnical structures, especially when passive anchors are involved. So thank you for your attention.
Allô? Ça marche? Oui. Thank you. Thank you, Jean, for this comprehensive study, including both physical and numerical study. Is it only your PhD work, or you have worked on this since then?
The only thing which is new is the abacus, taking into account the stiffness of the soil. So during the PhD, we considered the fixed parameter of the soil, and later on we added the stiffness abacus.
You're still working on this?
Not yet, but I still plan to work on it.
We have time for 2 or 3 questions. Just give your name, please.
Thank you. Jean-David Verne. What were the cohesion and friction values for the actual wall you worked on?
So for the modeling in centrifuge, we took a purely frictious soil, but the real wall has 8% of fine particles. the cohesion measured on in-situ testing gave 6 kPa, but actually my guess is that very soon the cohesion disappears, and so I considered in all the computations that cohesion was equal to 0. It does not change a lot the result in Prosper. I don't remember, I think in the paper of RFG I plot the result with 0 kPa and 6 kPa, but it does not do a huge difference.
It's because for that type of method, normally you need cohesion or a very strong arching effect if you don't want to have problems on site. So is this realistic?
Yeah, clearly on the and it's a problem also in the construction phasing, but clearly on site, during the excavation, you had the time to do the next excavation before the cohesion disappears, and I don't know what I put in the word disappear. So, but also when you have a lower cohesion, what you do generally is you, instead of excavating the whole band of your lift, you just excavate one block, you do the facing, another block, you do the facing, but it also changes the construction phasing.
Thank you very much.
Okay, Patrick, numéro. Did you have access in the centrifuge tests to the shear force, so the measurement of shear force in the nails? No? No,
it was only
okay.
The nail was 2 millimeters diameter, and so we were only able to put an optic fiber at the center, as a neutral fiber of the nail, and we only got it's a bit too small to be able to measure the
only the tensile forces.
Yeah.
Okay.
But in the numerical models, the shear force are quite low, and it does not change a lot the result of if you consider flexible or not flexible.
Yannis Anastasopoulos from ETH Zurich. Thank you very much for a very nice presentation, and especially the centrifuge test. I enjoyed it a lot. I liked very much that you mentioned the scale effects that you may have because of grain size. We did some pile tests, and there we had the same problem, so I think it's very similar. And actually what happens is that the mobilization is a function of the grain size, which we are not scaling down, which means that in the centrifuge you will have the same mobilization, let's say, displacement as in reality. And another difference we saw in the piles, at least, perhaps it is also applicable here, is that the dilation that takes place in this shear band is also much larger in the case of the small model, let's say, because the shear band is comparable to your structural element, while in reality your structural element is, let's say, much bigger compared to the shear band. So the trick we applied in this case was to model the centrifuge test with an interface that captures what's happening there, validate the model, and then go back to reality, changing the interface properties. So I was wondering whether you think it's an analogous problem, and if such a methodology perhaps could be of interest.
Yeah, I think it's really an analogous problem, and generally that's something we don't like to talk about when we do centrifuge modeling, because it's it's not it's maybe a black angle of centrifuge modeling. What we did is I said we get a repetitive law, but it was what I presented was it had the good shape of a friction law, but it was not actually the comparable value of QS and especially the stiffness before QS. So to change it, we glued some cement on the nails to change the rugosity of the nails and modify accordingly the friction law. But of course, you're right, it depends on the grain size, and the problem is the friction law is always given as tau as a function, the friction stress, as a function of the displacement, the relative displacement, and the problem is the relative displacement is obviously not kept constant when you go to the model scale. So and I think it's a very interesting problem that we have to work on.
Thank you very much.
Thank you. One very last question. Yeah.
Thank you very much for your presentation. As well, was thinking about the design implications of your work, because when you use just limit equilibrium or limit analysis without any addition, as you did, you get an overall safety of the system, irrespective of the actual distribution of the forces in the nails. So once, on the other hand, you are capable to predict nail by nail the actual force that develops under working load condition, then perhaps you are, I mean, what's wrong with the first way to do, and why do you really need the exact distribution in the nail if you can guarantee an overall stability with a sufficient safety or safety margin?
No, it's a very good question, and I think it's a question I answered to myself only at the end of the PhD. I think to design just the stability analysis of the soil nail wall, there is no problem with the multi-crayon method. Maybe we can find some problems, but and when Prosper was developed, there was a paper which stated that if you reach an optimal design, Prosper on the multi-criterion method gave the same optimal design. So the question was, to my opinion, was more important for the design of facing, because with the initial tension we got, you ended up with very stiff facing. I find it also a problem to have very stiff structures, because soil nail walls are quite not stiff, soft. So it's a good way also to resist earthquakes, and it's, I think, a shame to over-design the facing or even to over-design the length of nails. So yeah, the main question was actually regarding the facing design, and for the stability of the wall. If you reach an optimal design, you have the same thing. And if you have not an optimal design, since Prosper is still limited by the multi-criteria, you will be in the direction of safety with Prosper. So, thank you for your question.
Thank you very much, Jean, again. And I think now it's time to hand the floor to Roger Franck and Suzanne Lacasse.
Thank you very much.